Hello and welcome back. In this video, we'll be discussing the ideal gas law. However, before we begin discussing the ideal gas law, I first need to introduce the concept of a mole. So it turns out that there are a lot of properties of gases that depend on the total number of molecules that are present. For example, pressure and volume both depend on this. However, because molecules are so incredibly small, there is an enormous number of molecules in any macroscopic amount of a gas. And to deal with these extremely large numbers, chemists have introduced a concept that is called a mole. So 1 mole of any quantity is equal to 6.022 times 10 to the 23rd molecules, where this number, 6.022 times 10 to the 23rd, is referred to as Avogadro's number, which I'll denote with a capital N and a subscript A. So when we're working through equations, I'll be using the following notation. I'll use a capital N to refer to the total number of atoms or molecules in the system, and I'll use a lowercase n to refer to the number of moles. Now, because 1 mole is equal to Avogadro's number of molecules, if I have n moles, the total number of molecules is the number of moles times Avogadro's number. So this equation right here gives us the relationship between the total number of molecules and the number of moles. Now, one thing I want to point out about this notation that's very useful is that I use a capital N, so a big N, to refer to a very large number, right? The number of atoms or molecules will be a very large number, and the lowercase n, the little n, refers to a relatively smaller number, the number of moles. And it turns out that this is a convention that is going to carry over through several other quantities that I'll introduce throughout these videos. Now, because there is no way to directly measure the number of molecules that exist in a gas, we need to find some indirect way of getting at this information. And one way we can do this is by measuring the total mass of a gas. Now, because molecules are so incredibly small, the mass of an individual molecule will be minuscule. So oftentimes we'll talk about the mass of a mole of a substance. And the mass of 1 mole of a substance is referred to as the molar mass, which I'll denote with a capital letter M. And whenever I'm referring to a single atom or a single molecule, I'll use a lowercase m. So this is in keeping with this convention of a lowercase number referring to a very small number and a capital referring to a very large number. Now, the molar masses can be found on a periodic table of elements. So I have shown here like one little square that would appear in a periodic table. So you'll see that elements symbol usually appears either in a big letter here in the center or off in the corner, and then the mass is usually here in the center. One thing I want to point out about the masses that you find on a periodic table of elements, if you remember the very first video that I recorded for this class, I mentioned that chemists use a system of units referred to as CGS units. And that stands for centimeters, grams, and seconds. So because chemists use grams, the molar mass that you find on a periodic table of elements is measured in units of grams. And because we use kilograms in physics, you have to remember to convert this number into kilograms before you plug it into any equation. So let's go ahead and look at an example. This example asks, how many moles of water molecules are in 1 kilogram of water? So you may remember that water is equal to H2O. And what this means is that there are 2 hydrogen atoms and 1 oxygen atom in every molecule of water. So the first thing we need to do is we need to find the molar mass of hydrogen and the molar mass of oxygen. And the way we do this is by looking at the periodic table. So if we look at the periodic table of elements, we'll see that hydrogen has a molar mass of 1 gram per mole, and oxygen has a molar mass of 16 grams per mole. Now, because each water molecule has 2 hydrogen atoms and 1 oxygen atom, the molar mass of water, that's the mass of 1 mole of water molecules, is going to be twice the molar mass of hydrogen, because there are 2 hydrogen atoms, plus the molar mass of oxygen. So this is 2 times 1 gram per mole plus 16 grams per mole. So the molar mass of water is equal to 18 grams per mole, or 1.8 Now remember, grams are 10 to the minus 3 kilograms. So I've got a factor of 10 from that. So we have 10 to the minus 2 kilograms per mole. So remember that, let me go ahead and write this over here. So the total mass is equal to 1 kilogram. And the mass of n moles is equal to the number of moles times the molar mass. Right? So this is the number of moles times the mass of 1 mole. So I'm trying to solve for the number of moles, so I take n is equal to 1 kilogram divided by the molar mass for water. And if I plug this into a calculator, so if I take 1 kilogram and then I divide it by this number, 1.8 times 10 to the minus 2 kilograms per mole, I'll see that this is equal to 55.6 moles. So this is how many moles are in 1 kilogram of water. So now I'd like to introduce the ideal gas law. And an ideal gas, as its name suggests, is an idealization of real gases, and there are assumptions that we make about ideal gases that help simplify the equations that describe them. And the assumptions that we make about an ideal gas are: we assume that the molecules inside the gas are in constant motion. We also assume that these molecules have zero volume and that there's no interaction between the molecules in the gas. So this means there's no attractive forces or repulsive forces between these atoms. We also assume that the only thing that the molecules of the gas interact with are the walls of the container that the gas is in. Now, the ideal gas law is an empirical law, which means that it was discovered through a series of experiments. Now, I don't want to go through the whole history of the ideal gas law, but I do want to talk about two of the laws that led to the development of the ideal gas law, and then I want to show how these two equations can be combined into something called the combined gas law. And the two laws I want to look at are Boyle's law and Charles' law. So basically, what Boyle's law says is it says when the temperature of a gas is held constant, the pressure of the gas times the volume of the gas is equal to a constant. Similarly, Charles' law says that when the volume of a gas is held constant, the pressure of the gas divided by the temperature of the gas will be equal to a constant. So now I want to show how these two equations can be combined together to a single equation. So we have that the pressure times volume is equal to a constant only when the temperature of the gas is equal to a constant. And what this means is that because this equation is only true when the temperature is held constant, this means that this constant over here must depend on the temperature of the gas. If this didn't change, if this constant over here didn't change when the temperature changes, if this was always the same number, then we would just say pressure times volume is equal to a constant, and we wouldn't bother specifying that this is only true when the temperature is held constant. The fact that this is only true when the temperature is held constant means that this number has to change when the temperature changes. Because this constant depends on the temperature of the gas, I can write this as P times V is equal to some function of the temperature of the gas. Right? So this equation is going to be true for some function f of t, where I don't know what that function is just yet, but I'm going to show you how we can calculate what this equation is. One thing I want to point out about this equation that I have written down is that this is always going to be true. So even when the temperature of the gas changes, we still have P times V is equal to a function of temperature. For some function of temperature, I don't know what that equation is yet, but I'll show you how we can get it. The other equation we have is that we have that pressure divided by temperature is equal to a constant when the volume of the gas is held constant. Again, we can make the same type of argument. Because this equation is only true when the volume is held constant, this constant over here has to depend on the volume of the gas. If this didn't depend on the volume of the gas, we would just say that P divided by T is equal to a constant, and we wouldn't bother specifying that it's only true when the volume is held constant. So the fact that this is only true when the volume is held constant means that this number over here has to change when the volume changes. So again, we could write this as some function of volume. So I'll write this as G of V. So now what I want to do is I want to combine these two equations. Because these equations are always true, I can combine them. And what I want to do is I want to solve one of these equations for pressure and plug it into the other equation. So I'm going to look at this bottom equation here. I'll solve for pressure and I'll plug it into the top equation. So looking at the bottom equation, I see the pressure is equal to temperature times some function of volume. Now if I plug this into the equation on top, I see that we get temperature times G of V times V is equal to F of T. Now what I want to do is I want to rearrange this equation. So on the left side I have things that only depend on temperature, and on the right hand side I have only things that depend on the volume. So if I do that, I have T divided by F of T is equal to, actually let me have volume on the left side and temperature on the right side. So if I do that, I have G of V times V is equal to F of T divided by T. And at this point, there's a really kind of a tricky thing, but a very important concept to understand, is that because this left-hand side only depends on volume, and because this right-hand side only depends on temperature, this thing has to be equal to a constant. And the reason is that, let me kind of show you an example. So because this is true for any pressure, I have the choice of plugging in any value for the volume and any value for the temperature. So one thing I could do is I could, for example, hold the temperature constant. And because this equation is true for any volume and any temperature, if I hold the temperature constant, what I'm saying is that G of V times V is equal to a constant. And this is true for any volume. Similarly, I could hold the volumes constant. Then F of T divided by T has to be equal to a constant because I'm not changing the volume. And that's going to be true for every single temperature that I plug in, right? So the idea is that I can plug in any number of volume, and I can plug in any number for my temperature, and these two things always have to be equal. So it doesn't matter. I have complete choice over the volume and temperature. I can make them whatever I want, and whatever numbers I plug into this, they have to be equal. And the only way that can happen is if they are always equal to the same number. So because F of T divided by T is equal to a constant, I see that F of T is equal to some constant times the temperature. So now if I plug this back into this equation up here, let me write it over here, I have that P times V is equal to a constant times temperature, or PV over T is equal to a constant. And this is called the combined gas law. So this is actually how you combine two different equations. So it's pretty easy to do an experiment where you show that P times V is equal to a constant when the temperature is constant. And it's easy to show that P divided by T is equal to a constant when the volume is constant. But it's a little tricky to combine those two equations because we have to use this trick down here, which is called separation of variables. It's called separation of variables because I separate the variables on opposite sides of an equal sign. So when we combine all of these equations, we'll arrive at something that's called the ideal gas law, which I have written here. So we have that P times V is equal to nRT, where P is the pressure of the gas, V is the volume, N is the number of moles, T is the temperature. Remember, I've talked about this before. When we talk about temperature, this is absolute temperature. So this is temperature that is measured in Kelvin. And this R here is something that's called the ideal gas constant. So the ideal gas constant, it turns out, has a value of 8.31. And to find the units of it, we can use dimensional analysis. So the ideal gas law says that PV is equal to nRT. And dimensional analysis tells us that the units on the left side have to be equal to the units on the right side. So we have the units of PV are equal to the units of N times the units of R times the units of T. So if I solve for the units of R, I see that R has units that are equal to the units of pressure times the units of volume divided by the units of N times the units of T. And I'm going to go ahead and rewrite everything in terms of kilograms and meters and seconds. So here, pressure is newtons per meter squared, so that's kilogram meter per second squared, that's a newton, divided by meters squared, so that's the units of pressure, times meters cubed, divided by moles times Kelvin. And if we look at this units that I have up here, so meters squared is going to cancel with two of these meters. So I'm going to have kilograms, and I'll have 2 units of meters, So I have kilograms meters squared per second squared in the numerator. So kilogram meters squared per second squared are units of joules. So in the numerator we have joules, and then in the denominator we have moles times Kelvin. So it turns out that the ideal gas constant has units of joules per mole Kelvin. So this is just what I was talking about before. It's important to remember that when we're dealing with the ideal gas law, the temperature that appears in this equation is absolute temperature. So that means that anytime you plug numbers into this equation, you have to convert them to units of Kelvin. And 0 degrees Celsius is equal to 273.15 Kelvin. So you just take the degrees Celsius and you add 273.15 to convert to Kelvin. Now, we can also rewrite the ideal gas law in terms of the total number of molecules instead of the number of moles of molecules. And the way we do this is we say that PV is equal to NKT, where this K that appears here is now called the Boltzmann constant, so it's a different constant. And we can find the value of the Boltzmann constant by comparing these two equations. So we have that PV is equal to nRT, and we have that PV is equal to NKT. So if I just divide these two equations, on the left side I have 1 is equal to, temperature cancels, so we have nR over nk, or nR is equal to nk. And because n, we've talked about this before, the total number of molecules is equal to the number of moles times Avogadro's number, so I could rewrite this as n times r is equal to, this is equal to the number of moles times Avogadro's number times k. So the n's cancel, so I have that r is equal to Avogadro's number times k, so Boltzmann's constant is equal to r divided by Avogadro's number. And if I plug this into a calculator, oh geez, I don't have it written down. Oh, there we go. It's equal to 1.38 times 10 to the minus 23 joules per Kelvin. So this is the value of Boltzmann's constant. Now another thing I want to point out about Boltzmann's constant is that it follows the same convention that I was talking about before for the lowercase and capital numbers. So this capital R, this ideal gas constant, is a relatively big number. It's 8.31, and we use a capital letter, capital R, to describe it. And this lowercase k is the Boltzmann constant, which is a much, much smaller number. It's 1.38 times 10 to the minus 23. So the Boltzmann's constant is a lowercase number, and the ideal gas constant is a capital. And another thing I should point out, let me just open up a blank screen here. It turns out that anytime you have big numbers and small numbers like this, it turns out that the big number is always equal to Avogadro's number times the small number. So for example, we have R is equal to Avogadro's number times K. And we have that the molar mass is equal to Avogadro's number times the mass of a single molecule. And we have that the number of molecules is equal to Avogadro's number times the number of moles. So all of these equations follow that same convention. We've got the capital letter over here on the left is equal to Avogadro's number times the lowercase number. So let's go ahead and look at an example. The first example says, before leaving to go home for Thanksgiving, you check the pressure in your tires. The temperature outside is 0 degrees Celsius and the pressure in your tires is 32 psi. After driving, the temperature of your tires increases to 20 degrees Celsius. The question asks us to determine the temperature inside your tires. So let me go ahead and open up a blank screen here. So the information that was given to us was that the initial pressure is equal to 32 psi, and the initial temperature is equal to 0 degrees Celsius. And we're told that the final temperature of the tires is equal to 20 degrees Celsius, and we were asked to find the final pressure. So the ideal gas law says that PV is equal to nRT. So anytime we have an equation like this, where there's only two variables that we're looking at, in this case pressure and temperature, and everything else is held constant, for example, N is being held constant because there's no gas escaping from the tire, and the volume of the tire is being held constant, so the only thing that's changing is P and T. So anytime you have an equation like this where there's only two variables that are changing, what you do is you take the two variables that you're studying that are changing, so in this case pressure and temperature, and you move them to one side of the equal sign, and then you take everything else and you put it on the opposite side of the equal sign. So if I do that, I see that P divided by T is equal to NR divided by V. And the reason we do this is that NR divided by V is equal to a constant. So if N isn't changing and V isn't changing, then NR divided by V is not changing either, so it's equal to a constant. What this means is that P initial divided by T initial is equal to P final divided by T final, because P divided by T is always equal to a constant. So now if I just solve for the final pressure, I see the final pressure is equal to the initial pressure times the final temperature divided by the initial temperature. Now at this point we have to be a little bit careful. Remember that when we're using the ideal gas law, we're referring to absolute temperatures. So I can't just plug in 0 degrees Celsius in here, right? That would give me infinite pressure. That's obviously not right. We have to convert these temperatures to Kelvin. So we have 32 psi times the final temperature. Remember, you add 273 to get the temperature into Kelvin. So if the final temperature is 20 degrees, then in Kelvin it's going to be 293. And the initial temperature is 0 degrees Celsius, so in Kelvin that's 273. So now if I plug these numbers into a calculator, I see that the final pressure inside the tires is 34.3 psi. So the pressure inside the tires really doesn't change a whole lot when you drive. So let's go ahead and look at one more example. This example says, a large cylindrical container holds an ideal gas. The container has a radius of 10 centimeters and a height of 20 centimeters. The lid of the container is formed by a massless plunger, which can move up or down. The question asks us to determine how far does the plunger move when a 100 kilogram mass is placed on top of the container. So here I've just drawn a picture of what's going on. So we have this 20 centimeter tall container that holds an ideal gas and has a radius of 10 centimeters. And initially it's just sitting there. And then we're going to place a mass on top of this container, and it's going to push down on the lid. And the question is how far down does the lid of the container move when we place this 100 kilogram mass on top of it? So I think I'm going to need a lot of space here. I don't think I gave myself any room, so let me go ahead and open up a blank sheet. So once again, I've gone ahead and drawn a picture of what we're looking at. So the idea is that initially the lid of the container is just sitting there, and then what we're going to do is we're going to place a mass on top of the lid of the container. And when we do this, the weight of this mass is going to push down on the lid. And the gas inside this container has to exert an upward force to stop the lid from falling down. So what this means is that the pressure of the gas inside this container will have to increase so that the force pushing upwards on the lid cancels the weight of the mass pushing down on the lid. So what we're going to do to figure out how far the lid falls down is we're going to have to relate the pressure inside this container to its volume. So the ideal gas law says that PV is equal to nRT. Now we're assuming that no gas is going to leave the container and the temperature of the gas is going to remain constant. So what we have is PV is equal to a constant. So all we need to do is figure out how the pressure of the gas is affected by placing this mass on top of it. And the way we do this is by looking at a free body diagram of these two lids. So let me go ahead and draw a free body diagram of the lid initially. So initially we have this lid here. And there's only two forces that are acting on the lid initially. We have the pressure inside this container times the area of the lid, and then we have a force pushing down, which is equal to the pressure of atmosphere times the area of the lid. And because this lid is initially not moving, we can say that the pressure inside the container initially, so let me write this as just P initial, has to be equal to atmosphere. So now let me go ahead and draw a picture of the free body diagram after the mass is added. So here we've got this lid here, and now there's going to be three forces that are exerted on the lid. Actually, let me go ahead and draw the mass on top of here too. So we have the weight of the mass pushing down on it. It's force due to gravity. We have pressure from outside of the container, so we have P atmosphere times the area of the container. And then pushing up, we have the pressure, the final pressure of the gas inside the container times the area of the lid. So if we set these two forces, or these three forces, so they cancel out, so that means we're saying the final pressure inside the container times the area of the lid has to be equal to the force due to gravity of the mass plus atmospheric pressure times the area of the lid. So now we have this equation that describes the lid, the pressure inside the container when a mass is placed on top of this lid. So now what I'd like to do is I'd like to relate these two equations to solve for the final volume of the system. So we have that P initial, V initial is equal to P final, V final. So what I want to do is solve for V final. So V final is equal to V initial times P initial divided by P final. And this is V initial times the initial pressure is atmosphere, and the final pressure is just this divided by the area. So it's mg divided by area of the container plus atmospheric pressure. So I know the area of the container because I was told it has a radius of 20 centimeters, so I can write this as V initial. Actually, let me rewrite this slightly. So the final volume, if we think about this, is equal to the height of the container times the area of the lid. And the initial volume is equal to the initial height of the container times the area of the lid. So these areas will cancel. Here we have the atmospheric pressure divided by mg divided by pi r squared, where r is the radius of the lid that was given to us, plus atmospheric pressure. So now all I need to do is plug all the numbers into this. So if I plug all the numbers into this, I'll see that the final height is going to be equal to 15.3 centimeters. So initially we're told that the height of the container was 20 centimeters, or wherever that was. Oh, I didn't write it down. But the initial height of the container was 20 centimeters. That's what I plugged in here. And now the final height is going to be 15.3 centimeters. So this means that the lid moves downwards by 4.7 centimeters. So this is the delta H, how far the lid moves down when a 100 kilogram mass is placed on the lid. And so at this point, I think I'd like to end the video on ideal gas law. And in the next video, I'm going to talk about something called the kinetic theory of gases, which starts to look at the microscopic properties of gases. So we're actually going to start to study the motion of the atoms and molecules inside a gas.